again, I'm Eugene, and I'm back for some more weird and wild problems that are a lot more unusual than what you'll see in your typical standardized math test. This time, 1 to 107, target 2. The Sloths are planning their invasion to destroy New York City, probably to give humans a taste of their own medicine. They plan to line up in rows, and each row must contain the same number of sloths except for the very last row. If there are n sloths per row, then the last row must contain at most n sloths and strictly more than n over 2 sloths. Given that s greater than 1 is the total number of sloths and that each row must contain at least 2 sloths, what are the sum of the first 6 values of s for which the rows must contain more than 7 sloths? When I say weird and wild problems, I really mean it. Not only are we dealing with sloths in rows, which is not a topic you'll see in its typical standardized test, but there's also lots of words with lots of notation. So I think a good first idea might be to figure out what this problem all means and stuff. I think I have an idea of being able to model those sloths. Unfortunately, I don't seem to have any sloths nearby, but I do have some counters that can make for a decent stand-in. So let's get to it. So I got these pile of counters. Each of these counters can represent a sloth, and I'm going to go put them into rows for each row except for the last has 2. No single file lines. So this is the case where n equals 2. And the instructions say that if they are n sloths per row, then the last row must contain at most n sloths and strictly more than n over 2 sloths. The last row does contain at most 2 sloths since 1 is less than or equal to 2, but in regards to the strictly more than n over 2 sloths, 2 over 2 is 1, but 1 is not strictly more than 1, so 2 does not work for n. Okay, now time to try n equals 3, or 3 sloths per most of the rows, or at least the rows except for the last one. So now, the last row has 1. 3 divided by 2 is 1.5, but 1 is less than 1.5. That does not work. Let's try n equals 4. Last row has 1 again, but 1 is less than 4 over 2, which is 2. Does not work. I'm going to go try 5 now. Hey, 5 works because 5 divided by 2 is 2.5. 3 is greater than 2.5. Okay, if you're noticing something with like the last rows and thinking that it's like related to some mathematical construct or something, it is. That last row thing, we're essentially working with remainders. So we have a total number of 13 of these counters, and 3 is the remainder when we divide by 5. Okay, saying these remainders is kind of tiring, so now I'm just going to use the new term called mod. And this is part of something called, well, modular arithmetic. So now, 13 is congruent to 3 mod 5 because 3 is the remainder when you divide 13 by 5. And now what we're basically saying is, for a number of sloths s, if we divide by n, we want the remainder to either be 0, which is at most n, or strictly more than n over 2. So, for the case where n equals 5, we want the remainder to be 0, which is like everything filled, or 3, or 4. Okay, in other words, 1 and 2, the remainder of 1 and a remainder of 2 just doesn't cut it. Okay, now I got some ideas on how to go back. Now back to the tablet. Okay, I'm back. And to summarize what I said earlier, if S is congruent to 1, 2, all the way to n over 2, except you're rounding down, also known as flooring it, mod n, then basically n will not work. And we want it to not work for 2, 3, 4, 5, 6, and 7 in order to force the row count for much of the rows to be more than 7 sloths. Okay. So for the mod 2 case, S is congruent to 1 mod 2, S is congruent to 1 mod 3, S is congruent to 1 or 2 mod 4, S is congruent to 1 or 2 mod 5, S is congruent to 1, 2, or 3 mod 6, and S is congruent to 1, 2, or 3 mod 7. Okay, now time to think about what numbers could work. So if a number is 2 mod 4, then it would be even, but we said it was going to be 1 mod 2. So that basically means we only have to worry about if S is congruent to 1 mod 4. If S is congruent to 1 mod 4 and S is congruent to 1 mod 3, then we must have S be congruent to 1 mod 12. Just think about it for a little bit. Consider how like 4 and times 3 are is 12, and 4 and 3 don't share common factors. So since S is congruent to 1 mod 12, it's going to leave a remainder of 1 when divided by 6. So we don't have to worry about the mod 6 thing. So now we just have the mod 5 and the mod 7 left to worry about. So now let's tackle the mod 5 first, since it's smaller. So if it's 1 mod 12 and 1 mod 5, then it's going to be, well, 1 mod 60. But what about 2 mod 5? Well, let's just keep adding 12 to 1 and see what this results. 1 plus 12 equals 13, nope. 13 plus 12 equals 25, nope. 25 plus 12 equals 37. Yeah, that works. 37 plus 12 equals 49, nope. 49 plus 12 equals 61, and we're already cycled back since it's over 60. Okay, if you seem to notice how like if you take like the 1 and then the 1, it will result in 1 that's only 1 value or something like that. Or if they're like 1 and then the 2 and then you're going just to the 37 and stuff. That's because that's something from the Chinese remainder theorem, where basically you notice how like 12 and 5 don't share a common factor. And you're basically taking like one of the two you're taking like a value mod 12 and then a value mod 5. Then you're only going to get like one value mod 60 that is going to work for both of them. And this is, and hence why there's only two values, 1 and 37 mod 60. And so we can make use of the Chinese remainder theorem to basically effectively narrow our search. Now we just have the mod 7 to work. Maybe let's make a t-table to organize our information. So 1 and 37. 1 leaves a remainder of 1. 37 leaves a remainder of 2. So So those work. But 1 is not greater than 1, so no. So 37 is the first value that work. Add 60 to 1 to get 61. 61 divided by 7, it leaves a remainder of 5, and that does not work. 37 plus 60 equals 97. 97 leaves a remainder of 6. That does not work. 61 plus 60 equals 121. You know what? Rather than divide by 7, if you're adding by 60, then you're essentially adding 7 times 8 plus 4. So the remainder is just going to go up by 4, and as well as some cycling. So 5 plus 4 equals 9, so there's going to be a remainder of 2. Hey, that works. Okay, we already got 6 values. So now we just add 37, 121, 157, 241, 337, and 421, which I'm going to go spare you the time by doing it on a calculator, since that's allowed in Target. And we get our total sum of 1314. And we are done.
Hi, everybody. This is Tim. Hope you're enjoying our videos. If so, you know what to do. Like, subscribe, turn on notifications, all that sort of thing. But what I'd really want to invite you to do is to send us an email at media@mathleague.org. Tell us which problems you'd like to see us cover next in our video series. Take care and see you in the next video.